So thank you again, Leandro, for the invitation. I'm very happy. I would be more happy to be there, but I'm happy to see all of you. And yes, my talk will focus on the Poisson equation and complete manifolds. And what I would like to speak about is are the a priori LP estimates of the Hessian of the gradient of the solution. So the talk is mainly based on this old paper in 2015, joined with my friend Batu Gunezu, because in that paper, our investigation started on these global W2P estimates. And I wrote recently an account of recent developments up to 2020 in this paper that you can find in arXiv. Actually, I have an updated version, but I'm waiting for a reply of for a report of the referee in order to put just one version on arXiv, an updated version on arXiv. Said this, in 2021, a huge number of beautiful, difficult, deep papers appeared. So, and some other are going to appear, I know this, so I would like to give at least an aside reference to some of them during my talk. So, despite of the fact that my talk will be based on something which is 2015, then, however, I will give some new insight due to the paper that are appearing in the last year. So I start by saying what you are not expected to hear in this talk. Let Mg be a complete Riemannian manifold. Its Laplace-Beltrami operator is represented by delta, and the local coordinate expression of the Laplacian is this one. Given a datum, a smooth function f, you can consider the Poisson equation, namely the Laplacian of u equal to f on this complete manifold. And a standard way to approach the study of this equation is to consider the green kernel of the operator. If you don't insist that the kernel is positive, you have always a green kernel, meaning that a fundamental solution of the Laplace equation, and you can form, at least formally, a representation formula for the solution, which is minus the integral of the datum against the kernel. So once you have some geometric conditions on the manifold, you can estimate this green function, this green kernel, and this reflects on estimates on the solution U. Okay. This gives, on the one hand, it gives you an existence theorem, and on the other hand, it gives you estimates of the solution. And this is precisely what I will not speak about. In this talk, I will focus on this a priori global W2P regularity for a smooth solution of the Poisson equation and complete manifolds without any explicit reference to the green kernel. So I will assume that the solution exists, and I will try to show some methods useful to prove that an a priori estimate of this kind, so the LP norm of the gradient plus the LP norm of the Hessian, is dominated by the constant, which depends on the geometry, obviously, on M and the exponent P, times the u plus the LP norm of the datum F. So this resembles the classical Calderon-Sigma inequality from local irregularity. But what we studied was the global aspect of this inequality. And what I will put are a number of assumptions, a mix on an assumption on the geometry on the space and on the exponent P. These assumptions are represented by this A, B, C, D. And yes, just to have a look at what kind of assumptions they are. The first one is a lower bound on the Ricci tensor, and accordingly, we study the a priori estimates for P equal 2. So in the Hilbertian case, I will start from this situation because it's the easiest one, and one has a clear picture of what happens. A second set of assumptions is what is called B, and the geometry is bounded in the sense that Ricci is two-side bounded, and the injectivity radius of the space is positive. And in this situation, we can consider exponent that ranges from 1 to plus infinity. Another situation that I will consider is when you have a C1 control on the Riemann tensor. So Riemann is bounded in C1 sense. And it appears this very strange and as precise volume doubling condition, but I will comment on this condition later on. And this time, the exponent P is between 1 and 2. And finally, this is a work in progress joined with Stefano Meda from the University of Milano-Bicocca. We have another set of assumptions where you have a zeroth order bound on Riemann, but this time the P is large enough. So it is a puzzle. We don't have a clear picture of what happens for every P. And depending on the range of P, you have different kind of conditions. So what is important to stress is that switching from B to C and D enables you to avoid an injectivity radius assumption, which is not so natural in this context. So our research and also of other people went in the direction to remove this injectivity radius and put other geometric condition on Riemann, and this forces the range of exponent P to change. Okay, but this is just to have an idea of what kinds of assumption one has to put in order to have this kind of a priori in estimates. Why one has to be interested in these global estimates? So from the analysis of PDE's viewpoint, well, the Poisson equation of complete manifolds is interesting in itself. One could be interested in having a Calderon-Zygmund theory, a uniform Calderon-Zygmund theory for second-order analytic operators. And the question now is how much the geometry should be controlled in order to have this uniform Calderon-Zygmund theory. Other aspects concern with the submanifold theory. Yes, because if you take an isometric immersion of a Riemannian manifold into the Euclidean space, then the Hessian of the immersion is the second fundamental form, whereas the Laplacian is the mean curvature. So if you are able to control the LP norm of the Hessian with respect to the LP norm of the Laplacian means that you have an estimate of the second fundamental form with respect to the mean curvature. There are aspects related, very, very interesting aspects related to Sobolev spaces on manifolds. And here, what happens is that there is a tight connection between global a priori LP estimate of the Hessian, and the gradient and so on, and density problems in Sobolev spaces. So the fact that you have a density of smooth compactly supported function in Sobolev spaces is related, Sobolev spaces with involving two derivatives, is related to Calderon-Zygmund. Finally, I would like to mention, although it is not my peculiarity, there is another interesting operator theory, because this kind of inequality, global inequality, open new questions in the setting of covariant Ritz transforms on Riemannian manifolds. So it gives a new perspective in the study of this kind of operators on Riemannian manifolds. So just to have an idea of the possible interest in this theory. Is it okay so far? No, I don't hear you and don't see you. So.
Yes.
I suppose
everything okay.
Perfect. Okay, thank you. Yes, I would like to start, as I promised, with the L2 setting, the Hilbertian one, because it is the setting where we have a quite clear picture of what happens. And I also give a sketch of a scheme that I will try to use also in the Banach case, so when P is different from 2. And for the moment, I also suppose that the manifold is compact, and I take a solution of the Poisson equation, Laplacian of U equal F, and I integrate by parts this equation, the first thing that comes to mind, integrate by part this, use Young inequality, and you end up with an L2 estimates of the gradient that looks like the one in the box. So the gradient of U, the L2 norm of the gradient, is estimated in terms of the L2 norm of the function and the L2 norm of its Laplacian. And what is important to point out here is that curvature plays no role. So in the constant here, epsilon, you can avoid this epsilon by any choice you want. But the constant does not depend in any way on the curvature. This is a non-trivial fact related to functionality aspects of the theory. I will come back later on this point. So L2 gradient estimates, you get them by integration of the equation directly. In order to get Hessian estimates, so L2 Hessian estimates, the most natural way most natural strategy you can follow is to integrate the Bochner formula. So we are in a compact situation, so Ricci is lower bounded, let minus chi squared the lower bound of the curvature, plug in the Bochner formula and integrate twice. Again, the most natural thing. You apply, Young inequality, and as above, you end up with this boxed inequality. So the L2 norm of the Hessian is this time controlled by the L2 norm of the function again, the L2 norm of the Laplacian, but this time the curvature appears. And the fact that the curvature appears here, and then you are considering this lower bound Ricci, is not a matter of the technique you are using. So there are deep reasons why here you have in the L2 setting a Ricci lower bound. Okay. So so far so good. Two remarks. The first one is that the two inequalities I obtained can be summarized by saying that the W22 norm of the solution of the function on this compact manifold is bounded by, is estimated by the W2, is estimated by the L2 norm of the function, the L2 norm of its Laplacian. Okay, this is the typical form of Calderon-Zygmunt theory, where the constant depends on the Ricci lower bound. And the second remark I would like to put is that everything works if you avoid the compactness of the manifold, but instead you require that your functions are compactly supported. Okay, this time you have not for free that Ricci is lower bound. You have to ask it. This is a condition, but as soon as you ask that Ricci is lower bounded, everything works on any manifold up to using compactly supported functions. Okay, natural question now is, what about the genuine L2 setting? So far, we have considered only compactly supported function on a complete Riemannian manifold with Ricci curvature lower bound. Is it possible to extend the theory to the L2 setting? And the answer to this question is yes, but switching from compactly supported to L2, at least to me, is not completely trivial. Let's start with the gradient estimates. So how one can switch from compactly supported to L2 with respect to the gradient of the function. But the key observation is the seminal paper by Strickart in 1983, showing that in a complete Riemannian manifold, the Laplace-Beltrami operator is essentially self-adjoint. So this means that the maximum domain of the operator coincides with the minimum domains of the operator. What are them? Take a function u whose distributional Laplacian is in L2. This means that the function belongs to the maximum realization of the Laplace operator. Then, due to this equality, you have that u belongs to the domain of the minimum realization. This means that this function can be approximated in L2 by compactly supported functions. So there exists a sequence of compactly supported functions such that this sequence converges in L2 to u, and the Laplacian of this sequence converges in L2 to the Laplacian of u, to this distribution. Okay, so on the other end, we can apply to each element of this approximating sequence the L2 inequality we obtained before, simply by integrating the equation. And due to the fact that we have this L2 approximation, we can pass to the limit. So this inequality extends to the L2 setting without any difficulty. So what is behind here is a function operator property of the Laplace-Beltrami operator on complete manifolds. And again, the constant does not depend on the geometry, but it is just a matter of completeness. The L2 Hessian estimate is much more delicate, and this time, as before, the curvature condition enters in the game, and then enters at several levels, not only at the compactly supported level as we saw before, but in many other instances. So in order to see how things work in this Hessian estimates, we have to introduce two Sobolev spaces. The first one, W2P, is the usual one. So you have a function in LP whose distributional derivative is up to the order 2 are in LP. And we have another Sobolev space, W tilde 2P, made up by function in LP whose Laplacian, distributional Laplacian, is in LP. What happens is that you have this chain of equality. So the space W tilde to 2 is, you have a density result. So it is the closure of compactly supported function with respect to its norm. This closure coincides with the closure of this compactly supported function with respect to the norm in W2P. And furthermore, this closure coincides with the first space, W22. So we have several equalities that brings you to the fact that these two spaces are in fact the same. W2P and W tilde 2P are the same, and you have density in these Sobolev spaces. The proofs of these equalities comes from different arguments. We have already seen A. A is the essential self-adjointness of the Laplacian. B is the fact that due to the L2 Hessian estimates, the original one that I show you for compactly supported function, we have that the norm, the W tilde to 2 norm and the W to 2 norm are equivalent, so they produce the same closure. Instead, C is much more delicate, and it depends both on Bochner, integration of Bochner formula, but also on the existence of special cutoff functions. This was obtained under Ricci curvature lower bound, essentially in Shen Yao Red Book in '94. But a new breakthrough on the theory was given by Davide Bianchi and Alberto Setti in a paper in 2018, where they showed that, in fact, Ricci lower bound is too much strong requirements. You can allow Ricci to go to minus infinity quadratically. Anyway, whatever you assume that Ricci is lower bounded, then you have a sequence of cutoff functions, so they are smooth, compactly supported in between 0 and 1, which tends pointwise to 1. Their gradients go to 0 uniformly, and their Laplacian is uniformly controlled. If you have these, then what you can do is to use point C, so the density that I showed you before, the density in C, and apply the Hessian estimates to the approximating sequence, and let take the limit for the J that tends to plus infinity. So you apply the L2 Hessian estimates to the completely supported approximants, and then let this approximate to the function u, and get the inequality you want. So what are the ingredients that I put in the slide so far? Are these one? So in order to have an L2 estimate of the gradient, you only need geodesic completeness because it is related to self-adjointness of the operator. If you want to estimate the Hessian, the L2 estimate, the L2 norm of the Hessian, that you need a lower Ricci bound, apparently. So I show you how to get the estimate for Ricci lower bounded manifolds. And this property, this estimate, is related to density in subole spaces. Density in subole spaces, in turn, rely on curvature. They want assumption on the curvature. This was not clear until recently, and I put here two very important papers in this field. The one is by Giona Veronelli in 2001, and the other one is by Honda, Mari, Rimoldi, and Veronelli, again in 2001, where they show that subole density may fail even under sectional curvature lower bound. Is amazing. So these are the ingredients I put so far in the game. Just to connect with the last remark, so density in subole space is related to Calderon-Zygmund, but density in subole space is related also to curvature, needs curvature. One may ask this question: is it possible, is it true that also L2 Calderon-Zygmund type inequalities at the global level depends on curvature? They really need curvature assumption. The answer is yes. We found it in our old paper in 2015. We discovered that there is a rotationally symmetric Riemannian manifold, so R2 with this metric. This manifold has wide unbounded curvature, is very wide unbounded. And on this manifold, you can produce a violating sequence. What I mean? You can produce quite explicitly, prescribing this warping factor, which oscillates more and more. You can find a quite explicit sequence of completely supported functions, smooth completely supported functions, which has for which the L2 Hessian estimates does not hold. So they violate the Hessian estimates. And why this is true? Because straightforward computations show you that the L2 norm of the function and the L2 norm of the Laplacian both depend on sigma, directly on sigma, so on the warping factor. So you can make this warping factor in between two, for instance, to R and R plus 1. But the L2 norm of the Hessian instead depend on the first derivative of sigma, of the variation, of this warping function. So using this oscillation, you can make this sigma prime very high by keeping sigma in this with this controlled group, and this enables you to violate the Calderon-Zygmund inequality. Okay, this was the idea of the example, but now we know more. We know more, much more. We know from a paper in 2001 that there is no hope to let Ricci go to minus infinity in a controlled way, and to have that the Calderon-Zygmund inequality holds, that the L2 Hessian estimate holds. They prove in using a similar method to ours that it is possible, given any way to for Ricci to go to minus infinity, to produce to build up this warping function in order to have a violating sequence. So the Ricci lower bound is much more, the role of the Ricci lower bound is much more important than the technique that it used it. So I started by saying that Bochner needs Ricci lower bound. Okay, it is needed. In some sense, it is very much needed. And okay, now the L2 picture is quite well understood. And the subsequent question is, what about P different from 2? In this case, Bochner doesn't help. And the machinery, with respect to the gradient estimate, the machinery of Strickard's concerning the self-adjoinance of the operator does not work as it is. So everything should be new. And I would like to start, instead of starting with positive results, I would like to continue with counter example in order to have an idea of what one should expect. First, I put this definition. I call CZ the Hessian estimate. Calderon sigma, we use this terminology, although the gradient does not appear here. So as I did for the P equal 2 setting, I switched the study into two parts, the Hessian and the gradient. They are considered independently. So now I will focus on the Hessian. And I call CZ these estimates of the Hessian with respect to compactly supported functions. Okay, first of all, we had an example for two-dimensional manifolds and for P equal 2. But elaborating on this example, Siran Lee was able to remove both these restrictions. So the counterexamples for widely varying curvature works even if the dimension is whatever you want, and if P is in between 1 and plus infinity. You have a counterexample in each of these situations. The counterexample is very similar to ours. Here, instead, we have something very new. Another breakthrough in the understanding is due to a paper by De Filippis and Zimbron. It is a preprint in 2019. They discovered that the Hessian estimates cannot depend uniquely on a lower bound on the sectional curvature, meaning that fix the dimension, fix an exponent P, they consider only exponents sufficiently large, but I will comment on this point in a moment, and fix a dimension, fix a P, then fix a lower bound for the curvature. Then you cannot expect that any manifold with this, in this situation, has a Calderon sigma with a constant that depends only on this data. And how they reach this, they obtain this conclusion. In this way, they use singular space theory. So their proof, in some sense, is synthetic. And they show that there is a sequence of compact Riemannian manifolds, smooth compact Riemannian manifolds, which are lower bounded. The sectional curvature is lower bounded. The diameter is uniformly bounded. But in each of these manifolds, in each one of these, you can select a smooth function in such a way that the gradient, the LP norm of the gradient, and the Laplacian are uniformly bounded, but the LP norm of the Hessian tend to plus infinity. This shows you that there is no hope to have a uniform Calderon-Zygmund theory with a sectional curvature lower bound. And the proof is a very, yes, as a breakthrough, as I said before. I'm checking the time. I will not have too much time. It is based on, on this singular space theory. The idea is to consider a singular space and a compact Alexandrov space, which is the limit of smooth compact manifolds that are, with non-negative sectional curvature and uniform bounded diameter. And this limit space has a dense set of singularities. And so what they did is to consider on the limit space a Poisson equation, Laplacian, infinity means in the limit space. It is not an infinite Laplacian in the sense of nonlinear operators. So you have this equation on the limit space. You can prove that there is a non-constant solution, and this solution is approximated by solution of the same inequality, same equation on each compact manifold. So they are able to prove this, and also using Morey, and this is the point where they use the exponent is large enough, plus the fact that the Calderon-Zygmunt in the arguing by contradiction only depends, the Calderon-Zygmunt constant only depends on dimension P and the lower sectional curvature bound. They prove that the solution of this sequence of approximating solution of the limit Poisson equation are the gradient of this solution is Holder continuous. Since this property passed to the limit, they obtain that the gradient, the norm of the gradient of the limit solution is Holder continuous. But, and this is the main result of their papers, they prove that at each singular point, the gradient of this solution must vanish. So since the singularities are dense, they conclude that the gradient of the solution must be zero everywhere. But this means that your function is constant, and this is a contradiction. So, incredible argument. It is an incredible argument that gives rise to development because, be careful, they don't produce a single manifold where there is a violating sequence of the L2 Hessian estimates, of LP Hessian estimates. They prove in some sense, in an implicit way, that the constant cannot depend only on a sectional curvature bound. But in subsequent investigation, there are a paper by Ludovico Marini, Giona Veronelli, and Onda Mari Rimoldi Veronelli. I already mentioned this before. They were able to localize, in some sense, the construction by the Phillips and Zimbron and move the singular part to infinity in order to have that on a single smooth complete Riemannian manifold with positive sectional curvature, you can produce a violating sequence. So this ends the story in some sense, because you have all that you want. And they also remove the assumption that P is greater than N with a very clever trick. Okay, the last, yes, you have also counterexamples that come from the fact that Calderon-Zygmunt is closely related to implies, in fact, density in subwhole space. So any counterexample to density in subwhole space gives you counterexample to Calderon-Zygmunt. Okay, now we should have a more clear idea of what cannot expect. So we cannot expect to have sectional curvature lower bound, just sectional curvature lower bound. We cannot expect many things. Okay, now on the positive side, back to the whole paper in 2015. How to prove that some LP Hessian estimate holds, at least at the compactly supported level. But the very classical strategy is to what is called a local to global approach. So you take a ball. You try to prove that on this ball, say Euclidean, meaning that it is comparable with the Euclidean ball, you have an LP estimate. And you suppose that this ball is small enough that the metric coefficients of your Riemannian metric are sufficiently controlled in C1 sense. This enables you either to transplant the Euclidean inequality to your ball in the manifold, or by hard analysis, this is a really hard analysis, to prove directly that your estimates hold on the manifold, on this ball. You are able to do this for uniform elliptic operator. These are sensitive of the curvature and so on. You have a control on the coefficients of the metric, and so you are able to say that your inequality, in fact, holds on your ball in the manifold. Okay, it could happen, and we will see in a moment why it happens. It could happen that some ghost gradient terms appear, annoying gradient terms appear, so you have to get rid of that, but you can. And after you have this inequality on balls, and you suppose that these balls or fixed radius cover your manifold in such a way there is a uniform intersection multiplicity, then in order to have a global one, you have just to sum up everything, no? Yes, this is all. This is we have just to build on this single step. To be careful to implement these single steps, but it is a classical strategy to prove such a global integral inequalities. Here I mentioned in the remark that this strategy is the most natural one, but it is also useful to to deal with maps between Riemannian manifolds. Here we are considering only functions, but we can consider also Lipschitz maps between Riemannian manifolds. Anyway, okay, let's implement the strategy. I have 15 minutes, right? Something like that.
Yes, 15, 16.
Oh, okay, 16. Oh, wow. And so let's start with the Euclidean Calderon-Zygmunt. Some very clever guy did the task for us. We know from Calderon-Zygmunt that Hessian estimates exist in the Euclidean space, and more general for uniformly elliptic operators. The typical approach, one of the typical approaches, is to estimate the green function of the green kernel of the Euclidean space. There are other approaches, due, for instance, to Stein, who uses singular integral. No, he uses Ritz transform. In fact, he was I think the first who used Ritz transform methods. And there is also another approach due to Caffarelli, who was interested in nonlinear, fully nonlinear operators that apparently this was re-elaborated by Li Wang subsequently, and it works very well on manifolds. So it is very well adapted to be implemented directly on manifolds. So I put this reference here because of this. So in Euclidean space, we have everything. Now we have to control the metric coefficients. We would like to have the Laplacian in the form of a pure second-order operator, no first-order terms. And we also like to have a C1 controller of the metric coefficients. So this is the realm of harmonic radius, of the harmonics radius. I put here a plethora of radii just to impress, first of all, me and then the audience. So there are many choices of the radius that you can do. There is the classical conjugate radius, meaning that the exponential map is in the immersion. The injectivity radius, when you require that is a diffeomorphism. Euclidean radius, when you require that the metric as a quadratic form is comparable with the Euclidean one, and so on. What I would like to stress here is the harmonic radius. So what does it mean? Harmonic radius is the supremum of the radii of balls in the tangent space, of balls in the manifold centered at X, such that you have a coordinate system made up by harmonic functions. So the coordinates are harmonic. And in particular, this gives you that the Laplacian is purely second order. And moreover, you have that the metric coefficients are controlled up to the order 1, actually 1 plus alpha. So they are C1 controlled, and then you have a holder control on the first derivative of the metric. And it is well known from works by Anderson, first Jost and Karken in 82, and then in Anderson in 19, who realized that Ricci is enough to do many things. They say that in order to estimate this radius, where you have the C1 alpha control on the metric and you have harmonic coordinates on this ball, it is enough to have a uniform bound of Ricci and positive injectivity radius. So this is a non-standard version of their results, but you can recover the original results from this formulation. Okay, yes, these are comments. Yes, we are now able to transplant the inequalities once we have this control on the metric coefficients, because in coordinates, the Hessian has this expression, so you have second derivative is of u, and then the Christoffel symbols appears, but Christoffel depends only on the metric and their first derivative is. The Laplacian has this form, I already pointed out this, and the gradient depends on the first term up to the zero order on the metric. And next, you also have this volume element. So if you have a C1 alpha, C1 is enough control on the metric, you can transplant the Euclidean inequality and get this. With one problem, the red part, so something unavoidable that you don't want appears, so this gradient. But yes, we have to take care of this gradient in order to have a pure inequality Hessian estimate, a pure Hessian estimate in the form we need on a ball of fixed radius. Okay, yes. You can do also, you can have also this kind of inequality on a ball with you can prove it also with the method of Caffarelli and Lee Wang. This is what we are doing in a joint paper with Meda. It is in progress. Maybe I hope it will be finished very soon. But we will be able to build the Wang proof directly on a manifold, showing that if you have a sectional curvature bound, this time sectional curvature bound, then up to choosing P large enough, you have the inequality you want on a ball. Okay, no gradient term appears here. Okay, there is a P large, but it was communicated by Baptiste de Viver and Batu Gunesu that they have an interpolation argument in order to lower the exponent to 2. So actually, if you have this for large P, then you have this, according to the L2 inequality, you have this inequality for P in between 2 and plus infinity. Okay, so now we have to get rid of the gradient term. We did it using what is called usually the interpolation inequalities, meaning that you estimate the LP gradient, the LP norm of the gradient of completely supported function with, in the worst situation, the LP norm of the function and of the Hessian. If this is always true for P greater than or equal to 2, if P is in between 1 and 2, then you can do better. You have what is called multiplicative inequalities, and but you have the same. You can bound the gradient of U, the LP norm, with the function, and this time the Laplacian. So they are best with respect to, they are better with respect to the first one, the previous one. Or in the case P greater than or equal to 2, it is just a method of integrate by parts. Everything very, very elementary. The other situation instead is much more complicated, less elementary. The original proof used its kernel arguments, but now we have a more elementary proof, meaning new direct elite proof in the usual paper. Usual means that Honda, Mari, Rimondi, Veronelli, and so on, that I mentioned several times. So now you have, at least from my viewpoint, a more clear picture of why this estimate should be valid. Yes, so here we are in interpolation. So you can, in the previous slides, we had this red part. Now we are able to throw away this gradient thanks to the interpolation inequality. Here I put some other observation on the use of the interpolation inequality. Skip this. We can sum up the local inequalities. We are ready to sum up everything. It is a classical result by Gromov. Then once you have a local doubling, uniform local doubling inequality, then you have a covering by balls with finite intersection multiplicity. So the program can be completed in the sense that what you have built on a single ball, you can reproduce it on this ball of the covering and sum up each contribution, and you end up with the inequality you want. This is the local to global proof, classical local to global, but with some interesting insight in new future. And the last part I would like to mention, at least to mention the other approach, which is function analytic. The idea, I would like to move only at the formal level. The idea is to use what is called Ritz transform. So what is Ritz transform? Is an operator which is the gradient of the Laplace, positive Laplace, to the power minus 1/2. This is understood in the spectral sense, in the spectral calculus sense. And we have this operator for functions, but we have this operator also for forms, where nabla here is the covariant derivative, and Laplace 1 means that the Hodge Laplacian. So these are called the Ritz transforms. And the strategy in this setting goes as follows. So what you need is this estimate here. The Hessian, so the covariant derivative of the differential of phi, the LP norm, would like to be dominated by the LP norm of this operator, minus Laplacian plus k plus 1 of phi. It is equivalent to the inequality we want. And now what you can do, formally, you take the inverse of this operator and put on the other side. So this is equivalent to this estimate. Now the inverse of the operator can be written using spectral calculus as the composition of the operator to the powers minus 1/2 composed with itself. And the magic happens here because you have a commutation rule for these two operators. So the differential, the exterior differential, commutes with this. And then what you get is that you obtain your estimate, your needed estimates, up to be able to estimate these two covariant, to prove that the Ritz transforms are bounded operators. And so you have another fields of math that helps you to get these estimates. The second one is the classical one by Bakri. The first one is more recent, and there is a lot of work, currently a lot of work on this stuff. If you are able to prove the Ritz transform is LP bounded, both for function and covariant, you find geometric condition ensuring that this holds, then you have your Calderon-Sigmund theory. And you end up using this strategy with this part of the result. So when you have a Riemann bounded at the C1 level, you have this very strange volume doubling condition, because we are using here as a black box these results on the estimates on the Ritz transform as a black box. We use this in this way. But as I told you before, there is a research in this field. Gilles Carron announced that he is able to prove that covariant Ritz transform holds with Riemann that decays quadratically, and finally the volume growth condition can be removed. This condition B can be removed using very complicated arguments, under my viewpoint. And this is a preprint by Baptiste de Viver and Batoguneso. They told me that how they are able to remove this assumption and have a pure, a beautiful result, a pure geometric result in this field. I think my time is finished.
No?
Yes. No, I have
No, I have
some more minutes. Perfect.
Yeah, a couple of minutes.
Yes, so I would like to conclude. Just I skipped this, which is the how to obtain global LP estimates. So not completely supported, but and I would like to mention one point concerning the gradient, because I switched. I obtain estimates in a separate way for the Hessian and for the gradient. So far, I told you something about the Hessian, but what about the gradient? Here, the situation is more obscure. There is this surprising result by Milatovic saying that what Strickart did for p equal 2 actually holds in any p, for any p. This is surprising. It is operator theory. But more important for our setting, recently Chen, Thalmayr, and Thompson proved that if you have a Ricci lower bound, then you have the gradient estimate at the LP level. So you have a function u, smooth function, you can consider smooth functions, which are in LP, whose Laplacian is in LP, for any p in between 1 and plus infinity, then the gradient of this function is in LP, and you have this estimate with a constant that depends only on the Ricci lower bound. This is, in my viewpoint, a very nice observation. They obtain this with very refined probabilistic arguments. Today, we know at least two other proofs of this, one using operator theory, and the other one using PDEs, using a PDE viewpoint. On the other hand, it is still obscure whether or not the Ricci lower bound is needed to get this kind of estimates. So I think this is a point that deserves some more research, because, okay, gradient estimates are useful in geometric analysis. Yes, and now I finished my presentation. Thank you very much for your attention.